G'day folks, this is my workshop, which is also my shed, and in addition to doing a little bit of work at school, I'm going to be doing some videos from here to show you a range of projects, bits and pieces that I've been working on here at the shed. Some of the stuff will be for school, some of the stuff will be projects that you would have otherwise been doing at school, and some will just be different things that show some interesting skills that sort of relevant to what we do here. So the first thing I'm going to do, just a straightforward small project, I've got my lathe here. This is a Hercus 260. It's similar to the Hercus 9-inch that we have at school. This one's got a slightly higher swing above the bed, so the center of the chuck is half an inch higher, I believe it is. And the bed's otherwise the same. Most of the other bits and pieces are fairly similar. It's got a much nicer headstock. This one comes with roller bearings, which is really great. It's got roller bearing headstock, belts and all that. It's pretty similar to the Hercus 9-inch, very similar setup, just a bit more compact. This one also, over the ones we have at school, has a quick change gearbox, which is really snazzy with the kit. You can use that to adjust how fast the drivetrain works for the lead screw, so you can adjust feeds and speeds and do all sorts of nifty things to make the lathe work a bit nicer. So it's a higher spec model than the one we have at school. It's also more recently manufactured. One's at school in 1967, I think, from memory, manufacture date. This one was made in 83, I think, something like that. It's a fair bit newer, and it's in much nicer condition because of it. Now, one of the things I don't like about this lathe, down here on the tailstock, we've got the locking lever and got this little knob on the end. I'm not a big fan of that. It's kind of an ugly shape and looks a bit crap. It doesn't really suit the rest of the lathe. So what I'm going to do is take a piece of brass, right there, and I'm going to turn that into a sphere. Now, I've made a special tool a few years ago to turn spheres. It's an attachment that can't even go on the lathes at school. But to do that, we need to work out a few little bits and pieces to hold the workpiece while we turn it into a sphere. And there's a few steps involved in making round spherical objects on a lathe. So I'll set up for the first part of this job and we'll get started. So the first part of the problem is that we need to work out what the inside of this knob actually is. It's usually, and this one is, it's usually threaded onto the end of a stud. This one's had a bunch of thread locker. It's got that schmutzy stuff left all over the threaded shaft in order to have that stay on there. We're going to be making this replacement knob out of brass, and brass tends to lock onto shafts pretty well anyway, so won't need to worry about thread locker. One of the jobs we'll have to do is to get a small wire brush and clean this shaft up so that the replacement knob will fit on nice and neat. This knob here has a threaded hole, of course, to thread onto the end of the stud, and we need to know what size that threaded hole is. There's a couple of ways we can do that. You can measure the knob itself, as in measure the inner diameter and try and work our way back out from there. You can also measure the pitch of a thread inside a hole, but it's really awkward and difficult to do. It's fraught with problems to get it accurately done, and we're lucky enough that we've got the male component of the thread just here ready to go, and we can measure that and determine what thread it is that we're working with. So I've got here my vernier calipers. This is a bit tricky to do behind the camera, but bear with me. I'm going to put them on a bit of an angle so I get across a number of the threads nice and snug. I'm not trying to crush it, we just want the caliper to be on it correctly. And I'll see if I can get some focus. There we go. We're interested in the top scale. Top scale on vernier calipers is usually imperial threads. I suspect this is an imperial thread because it is a Australian made lathe, and it was originally designed and most of the specifications were worked out at a time when Australia was still largely imperial. I'm looking at a glance very quickly at the bottom scale. I can see that it's 9.5 millimeters, 9 millimeters past on the zero. The zero is past the 9 millimeter mark. And I look along the vernier scale. I can see that the 5 lines up pretty good. So 9.5 millimeters. I don't know of any commonly used threads that are metric that are 9.5 millimeters. M10 is quite commonly found, M8 is quite commonly found. I highly doubt it's either of those. I suspect it's imperial. So I've got here the 0 on top. It's lining up with the third notch after the 3. So it's lining up neatly with that third notch. I don't need to worry about the vernier scale across the top. Just need to worry about where that notch is with the 0. And that represents 0.075 of an inch. The 3 represents 0.3 of an inch. So it's 0.375. That confirms to me that this almost certainly is an imperial thread. It is going to be 3/8 of an inch, which is 3/8 is 0.375. I'm going to confirm that with a thread gauge, so let me get some equipment together and we'll move on to that next part. Okay, I've grabbed 2 more tools here. I've got here what is called a thread pitch gauge. This one has 16G 3/4 written on it. Not sure what the G refers to, but the 16 refers to the threads per inch in this case. The 3/8 is an indication of what standard size usually uses that pitch of thread. And in this case, that's what I'm suspecting this is. If I line up the thread gauge, see how it fits really neatly in, if I can get the focus, see how it fits really neatly in the thread. It absolutely is a 16 TPI thread. So it's imperial, it's 3/4 of an inch major diameter across the top of the threads. Let's just check for tits and piggles. The other pitches, we've got 14 here. 14 is a standard pitch for 7/16, I think. Get focus. Yep, 7/16. We'll check that on our screw. No, it's not going to fit. I can get the start in one end. It doesn't really want a bar of it. That's not the correct pitch. But the 3/8 16 fits perfectly. I can also double check that. If you don't have a thread pitch gauge, there is another way you can do that. You can use a tap. A tap is a way of cutting female threads. We're going to be using this tap here. This isn't from my collection. I've had to borrow this from school so that I can cut this thread. A tap is a good way to gauge what the thread on a male shaft is. If you just line up the threads just like you were using a thread pitch gauge, you'll see that the threads fit into that quite neatly. Now, I'm happy that that confirms my initial assessment that this is probably, or almost certainly, a 3/8 inch screw, 3/8 inch across the major diameter, and 16 TPI. Incidentally, they do write that on the tap. If we have a look at the tap here, we have 3/8 NC, that's national course for UNC threads, Imperial American style, and 16 threads per inch. So now that we've identified that, I'm going to refer to a tapping chart that will tell me what size drill I need for drilling a hole for that tap to comfortably go inside and cut a thread. And we'll start doing that on the lathe. Now, a few little setup things that we need to worry about over here. I have my 3-jaw chuck. I'm going to be using a 3-jaw chuck in this case because the job doesn't require humongous amounts of precision. If we needed to hold this workplace in a very particular location, we would use a dial gauge on the circumference of the work, and we use a 4-jaw chuck so that we can independently move that workpiece around until we get it dead center. There is a hole in this piece of material already. I'm not certain it's on center, but it doesn't particularly matter again in this instance. Even if we get our center drill, we'll probably open up that hole and start trying to guide the next size drills up into that hole and on center. But if those holes don't go on center, not a massive problem in this particular case. Now, I've got a few other little issues to overcome here. This is a metric lathe. This is going to become a problem because I need to support this piece of brass on a threaded rod so that I can cut the spherical outside of the object. I can't cut a 3/8 16 TPI thread on this lathe. Not easily. There are ways in which you can do it, set it up to do it. It takes a great deal of work, and just for a little knob that's a decorative piece, not really warranted to go to that much effort. So what I'm going to do is drill a hole into this job relatively deeply for the 3/8 16 TPI thread, and then I'm going to drill a hole shallower that is a bit bigger that will allow me to thread this to probably M12 or M10. I might check M10 to see if I've got enough thread clearance in there to make sure I can still get both taps in there. I think I might, no, I'm pretty sure I'll run out of room actually. So I'll have to go to M12. M12 will be the second step of thread in that hole for the shallower part. I can hold an M12 thread. I can machine an M12 thread on this lathe, and then I can leave that in the lathe, thread on my piece of material, and turn the outside into a sphere. Then after that, I'll part off the M12 part that I don't need, and that will leave me with a ball with a 3/8 of an inch hole in the inside of it. So I've put my job in the chuck. I need to face it off. I'm going to swap tools. I've got here a parting tool in here. This is an insert tool, tungsten carbide insert. These get used an awful lot in the industry, and they're starting to become more common in hobby workshops and such now. eBay has them amazingly cheap. Industry tends to buy stuff direct from large, well-known manufacturers, and the quality would be a lot higher. You could pay for a pack of 10 inserts up to $100 fairly easily. On eBay, you get them much, much cheaper. So I don't need that. I'm going to run off this tool here. First thing I want to do is clean up the face, just so that I can work from that face and measure from it reliably. Most of this face will disappear later on, so that when I go to part the job off. I've got my speed set relatively high. Belt is that way, a fair way. I'm not in back gears. I'm running pretty high because it's brass. Brass will tolerate high cutting speeds. No need to run coolant, no need to run lubricants. Everything should work fairly nicely dry. So I'm going to face the job off. Just touched off. You can see this workpiece is actually pretty domed. It's quite curved. So I'm going to have to part it off, face it off just so I can get it back to flat. I'm doing a relatively rough job here. I'm not aiming for really high quality surface finish. This part of the material is going to be parted off later. Just want something that I can dependably measure from. Now it appears that that hole is pretty well centered, so I'm going to stick with that hole. What I will do though, to encourage drills to follow into that hole fairly well, is I'm going to run this center drill. Center drill in its own specific holder. This is a quick way to mount center drills rather than using a 3-jaw Jacobs chuck. I've made one for my two most commonly used center drill sizes. I've got a number 4 and a number 2. Use them a lot. Bring it up close to the job. Haven't done heaps there, but I have put a chamfer on the hole, and that chamfer will allow us to make sure that the correct size drill, which is an 8.5, will go into the hole exactly where we want it to go. So I'll get set up with the drill and my collet chuck, and we'll come back. Good morning, folks. We've had a bit of a change of plan over what we were doing yesterday. Originally, I was working with a small piece of brass rod that I had rescued from my scrap box. It was a whisker over 1 inch. I think it was 1 1/8 of an inch diameter. Brass rod is purchased imperially. You can't buy metric brass rod. The size was a little bit on the small side. Not so much for the major diameter itself of the sphere. The sphere itself would have been an okay size, but the length of threaded rod on the tailstock handle meant that it would be a bit nicer to have a little bit more diameter to play with to cover the rod up properly. There's quite a long thread there, so in order to cover it, we need a larger sphere. So to that end, I've been shopping. Bought myself a lump of brass. I bought 1.5 inch diameter brass rod this time, which is a whisker over 38 millimeters from memory. This rod I purchased at 300 millimeters long, so as I need it in the future, I will cut pieces off it as I require, rather than just buying little tiny knobs from Collier & Miller. It's a bit of a pain in the backside to handle it. Now this rod is 1.5 inch nominal diameter. It's not particularly round. I'm not certain of the manufacturing process they use to make these rods, but it's going to come out at a whisker over 1.5 inches. So when you purchase rods, particularly hot rolled rods, they're going to be nominal sizes. So you might buy a 100mm rod, hot rolled rod, and it will come out at slightly more than 100mm. In this case, we've got 1.5 inch rod, and it's a little bit over 1.5 inches. There should be 1.5 inches of material inside the rod at all points. Usually, I haven't seen any in recent experience that have been undersized. They're always aiming to go slightly over, so you have material to play with. Now, this 300mm length is going to present a bit of an issue, because if I mount this in the chuck, which I'll do now, I mount this in the chuck, it's going to work out to be pretty long and dangling out in fresh air. Now, as I mount this, just for a little technical information, I'm going to tighten this up just a little bit and just jiggle the job in the vise, in the chuck rather. I'm just trying to find where it's happiest, sitting straightest in the material, and it gives me the best chance possible to get this rod nice and straight. I've got a fair bit sticking out here. I'm a little bit borderline for needing to support this end of the job in order to do the things I need to do. I would like to face the end first and center drill it so that I can support it. Once I've got it supported, then I'm able to come in with a parting tool and part off the chunk that I require for this job. I'm going to touch it off with the tool, see how it goes. If I get heaps and heaps of chatter, then I am going to need to set up a fixed steady around the job here, which is a bit of a pain in the backside, but it will mean that when it comes time to part, I'll have a lot more support. Now, always check the chuck is not going to foul in anything. I'm just going to eyeball this job, see how out of straightness it is. It's pretty good. Just out of interest's sake, we might bust a dial gauge out and have a quick look, see how straight it is. Don't know if you guys will be able to see this. A dial gauge, which I might cover in a bit more detail later on for other parts of this job. The dial gauge has a needle. Let's see if we can move around and have a look. Dial gauge will have a needle, and the needle will tell us how out of concentricity a piece of material is with the axis of the machine. Now we're getting some big-ish swings here. Probably 0.1 of a millimeter, 0.15 of a millimeter or so. That's okay in this case. I'm also seeing that it's kind of lumpy looking, which confirms this rod's not particularly round. It's round-ish, which is fine for what we're doing, but that's why they manufacture rods for nominal sizes. So it's straight enough for the process we're going to look at. I'm going to give it a bit of a test run. We'll see if we can't get it faced off straight and with a center drilled hole in the end of it so that we can support it to do the remaining operations we need to do. The other concern that I have is that my parting tool, my preferred parting tool, is not going to be anywhere near deep enough to part to the center of this rod. So I might start it with this tool and then complete the parting operation with a high-speed steel tool. First problems first, let's see how we go with facing off. We can't gently face this off. I have a pretty rigid chuck. This chuck isn't original to this machine. It's one size larger. It's a very nice chuck. It's a Czechoslovakian made chuck. Cost a fortune, cost more than the lathe did, but it's a very nice thing for holding workpieces. Let's see how we go. Gently, gently. I'm going to come in just using my compound to touch off. Not hearing any chatter. have a look. We'll see what we've got. A couple of little tiny nicks. I don't even know if they'll be visible on the camera. They're outside of the piece of material that we're going to end up using anyway. You might see, yes you can see on the camera, that there is a small little nub of material left in the center of that. Normally that would mean that I need to adjust my tool height. I have these insert cutters, which I mentioned before, and I have machined the bottom of them. If I get my parting tool, I've machined the bottom of them so that they are the correct height for my machine. The reason why this tool is not coming up on center correctly is because I have reground the tip of this tool so that I can do different types of work. I was machining a piece of stainless and I needed different tool geometry to what the insert offered me. So I fiddled with the tool shape on the very tip of it, but that come at the cost of height. My center height is now a whisker low. In this instance, it's not a major drama. I'm going to continue with it. Now, we would like to get a center drill hole in that. I'm going to use this. This is my center drill. I have a number 4 center drill. And I've made a special center drill holder. This is a nice little lathe project. If you happen to own a lathe, very handy to have your center drills in a dedicated holder. Means you can get them into the tailstock very quickly and get them out and continue on with your work. So, smack it in there. And she'll put a center drill hole. Get the tip of the center drill to clear in first. Now we've got a second set of angles on the drill. I want to go about halfway, 2/3 of the way up that second set of angles. Did get a bit of chatter there. That can happen with drills. If it does, they tend to like to be worked a bit harder. So I'm going to give it one last little push, a little bit more firmly than before. With some success. We'll have a look at the quality of the hole. It's okay. Might just give that a tweak by hand, just so I can get the surface finish to be a bit improved. That's probably why it was chattering. Chuck was coming off of the spindle. Yeah, it's not too bad. We'll roll with that. Give this and that a bit of a clean. Center drill can go away. And we shall set up for the next part of this machining. Okay, I've just moved over to my workbench. I'm just doing a quick little mud map or a whiteboard marker map on a scrap piece of steel that's lying around. Just to show the game plan of what it is I'm trying to achieve here. Now, the outside is going to represent our piece of material. It's going to be 38 and change because it's imperial rod. I anticipate that the ball will probably end up a good bit smaller than that. It will vary depending on how well I can locate the sphere. Turning spheres is a little bit of a fiddly process, as you guys will see. Now, I've got this extra section here. Imagine I've got my lump of material and I've cut it in half, which is called a section view. I need to have a section of material that I'm going to do a thread. I'm going to do an M12 thread. An M12 thread in here, if we imagine that. That M12 thread needs to be there in order for me to hold this workpiece whilst I turn the sphere. If I don't have an M12 thread, then I'm going to run out of material to hold on to as I cut this spherical profile. I'll part that off at the end. The last process will be to cut that off right there. And this part here will go in the bin. It's, well, probably back in my scrap box. It'll get used for other things if there's enough metal there left to play with. I'm left here with the sphere. It has another section of a hole in it. That is a different thread. That thread there will be, what is it, 3/8 we talked about, in C16. Now the reason I've got to add this 20mm thread is because my lathe is a metric lathe and not readily set up for turning imperial threads. I'm going to cut the thread on the lathe for the M12 thread so that I can guarantee that the thread form will be concentric to the center of the machine. So I'll turn the thread in situ where I want the thread to be and leave that piece of metal in the chuck and screw my piece of brass onto that threaded rod to continue doing my operations. That piece of thread will be done on probably a 16mm rod. I'll see what I've got in my box up on the shelf, and then it will be disposed of, or I can cut off the threaded end that I don't require anymore once I've finished this operation. So metalwork often can involve little jobs like this where you have to use a machine to create a fixture or some sort of tool in order to hang on to pieces of material that you need to work on. A good chunk of your time can be spent on work holding. It's a very difficult part of machining as a whole. It's not always going to be straightforward, like putting things in a chuck and just working on it there. Now, that's the plan of attack. I'm going to need to figure out how much material I need to part off as we're set up in the lathe here. So I'm just going to do a quick look at that. I'd like to have 20mm of thread. I have here 19mm of threaded shaft to accommodate. I'm going to need the thread to be a little bit longer because a tap generally doesn't thread right to the bottom of the hole without being modified. I have a bottoming tap. We'll talk more about that in detail in a future clip. But in this case, I'm going to need probably at least another 20, not 30, I'm going to need another 20 of threaded hole. I might even expand that a little bit further, to be honest. I might give myself 25. I think I have about 3 or 4mm of partially threaded length on the end of the tap. So 25mm should give me a little bit of extra space. That means I'm looking to dig a hole that's 45 deep. I'm going to want a little bit of extra depth so that I don't broach the end of my sphere open. So I'm going to give myself, let's go 5mm. So that gives me 50mm total material that I need to part off. I'm going to do the parting operation last. I think I might look at doing the drilling before I part the material off. At the moment I have a center drill hole in it that is concentric and on center with the axis of the machine. So now's a good time to go throwing drill bits through the center of that hole that's already in place, and they should end up on axis. Let's move back to the machine. So we've returned to our stock in the machine. We are a long way out from the chuck, as I mentioned before, which does make machining it difficult. If I wanted to parallel turn this piece of material down, I'm definitely going to need to support it in order to do so. At this point, we don't need to worry about that. First operation we're going to do is drill a pair of holes into the end of this shaft so that we can have 2 diameters left, one for our 3/8 of an inch thread, and we're going to leave a counter bore at the front of this hole with enough material left to cut a M12 thread, and that will allow us to support the work while we work on it. So we need to hold a drill bit in our tailstock. Tailstocks should already be on center with the machine if the machine is working happily. Normally what most people would do is move to a drill chuck like this. This is a Jacob style chuck. This one has a tapered shank on it for working on the milling machine. This one doesn't get used a great deal in my workshop. At school I do use them a reasonable amount for things like drill presses and less accurate work holding and tool positioning. These tools, Jacob style chucks, are fine. They don't clamp particularly hard and they aren't terribly repeatable like any 3-jaw style chuck. They tend not to be the most accurate way to hold on to tools in order to do work with them. They are, however, very quick, easy to use. Some of them even have no key. You can have keyless 3-jaw chucks. I tend to avoid those as well because they are self-tightening. So if you are using stepped shank tools, they can be problematic. You'll over-tighten the jaws in use of the drill bit. Not something I'm a big fan of. You end up needing to get pipe wrenches and abuse tools to get them apart. So we're not using that. I'm going to be using this. This is a collet chuck. Pretty simple little project. I made this one a few years ago now on the previous lathe, but this one has an MT2 shank already machined onto the project. It's got some flats, that's for a spanner to fit onto it, and a threaded section here. That threaded section accepts this nut. This is an ER collet nut. I'll just park that on the end of there for a moment. And this is the center of activity for a collet chuck. This is a collet. This is the front of the collet. This one is marked 8 to 7. That refers to its clamping range. It will accept any tool being put into that hole or workpiece. Sometimes you can hold workpieces in collet chucks from 8mm down to 7mm. That's quite flexible for a collet. A lot of other styles of collet don't have very wide clamping ranges at all. I know 3C and 5C collets, I believe, have something like a 5 thou clamping range. So if you put a 1-inch rod in a 1-inch 5C collet, then it can be acceptable down to 0.995 of an inch, which is not a huge range. 1mm is 39.6 thou, I think, something like that. Quite a wide clamping range. These are also very rigid, which is really, really useful, and they have very high clamping pressure. So any problems you might have had in the past where you have had drill bits spinning in Jacob's chucks, then moving to a collet chuck will eliminate those problems. The downsides, they are slow to use. It requires tooling. I have a pair of spanners here that we'll be putting on the collet chuck to tighten it up. It tends to make tasks a little bit onerous, but the benefits are worth having in my view. I much prefer this, especially for the home workshop where we're not here making money. I have an 8mm drill. I've referred to a tapping chart, and I'll put a link to that in the Google Classroom. It's a useful document if ever you go into the world of metalwork. I have a tapping chart that will show you where the relevant size of thread is that you're looking for and which tapping drill is appropriate for that thread. I've got an 8mm drill here, and this is for the 3/8 NC16 thread. 8mm isn't actually the prescribed tapping drill. We would ideally want a 5/16 drill. 5/16 converts to 7.94mm, so 0.06 of a millimeter difference. Not heaps. In this case, we can get away with that. So I don't have a 5/16 in stock in my shed. I'm not sure if I even have one at school, but 8mm will do fine in this case. Sorry for covering up the camera. Tighten up the collet chuck. We're going to drill this 45mm deep. First thing we're going to do down here on my quill, if I can move the camera, down here in the corner of the shot you'll see I've got some markings on my quill. I'm going to set that to 10mm. As the quill comes out, it will indicate how much of the quill has left the body of the tailstock. Gives me an idea of how deep I've drilled. It's generally only as accurate as any other ruler, so not terribly accurate, but in this case that will be fine. I'm looking to drill 45mm deep. So I may have to take another bite of this. Now this is quite a deep hole. At the moment I've got the chips coming out of the drill just fine. I'm getting quite a nice string actually, which is pretty unusual for glass. Drill bit's happy, so it's working well. At some point you might find that those chips don't want to come out of the drill bit flutes anywhere near as neatly or as freely as they once were. A 45mm hole is a fairly deep hole for a drill bit. You can see the chips on top starting to pack up. So I've just moved the camera here. You can see the chips coming out of the drill. Brass is relatively free cutting. It will do this fairly happily, but at some point you're going to find that the chips do not want to come out of the flutes anymore, even though I'm still advancing the drill. At that point I'm going to need to start evacuating the drill, continuing drilling my hole. Going okay at this point. Now I'm near the limit of my quill, which means I'm at about 40 millimeters. Just going to verify that. So move the quill out of the way. I'm actually going to need a bit of room here. I might remove my drill and collet chuck altogether. I want to see how deep I am at with this hole. Do need it to be clean. I'm going to use the depth measurement rod at the end of my vernier calipers here, just to get an indication. Stuff's in the way, it's not much fun. There we go, we've got enough room. Just to get an indication of how deep we are in this hole. I'm expecting it to be about 40 millimeters. Oh, couldn't have planned it better if I tried. 40 millimeters, if we can get focus. Focus. There we go. 40 millimeters. So we have 5 millimeters to go. I'll reinsert my chuck. I'm going to re-zero my quill measurement back at 10 millimeters. I couldn't do this whole hole. That's a terrible sentence. Couldn't do the hole with one hit because my quill travel is not sufficient for the job. 5 more millimeters. So that's the first hole done. So with that first hole done, we can swap out our collet and drill bit for the next size up. We're going to do a counter bore now that is 10.2 millimeters. 10.2 is the tapping drill for an M12 thread. This is one of the downsides of cots, is that I've now had to swap out from my, what was that one, 8 to 7 millimeter collet to a 10 to 11 millimeter collet. Collets do have very limited range, so using them, if you're going to use them in a serious way, you generally need to have an entire set, which is a bit of a pain in the backside. It's also a little annoying. This one here is a 10.2 millimeter drill, so we've got to clamp down 0.8 of a millimeter before we get down on this drill, and it does take a bit of turning and carrying on. Collets work a lot quicker if you're on the exact size, but that's not always possible. Now we want to do 20 millimeters of counterbore here. And it's important that we stick to exactly that measure because we're going to part off the end of the ball later on, and we need to remove that 20 millimeters exactly so that we're left with just our 3/8 NC16 thread inside. Now I'm set up to that. I've re-zeroed my quill. I've moved the quill and the tailstock up against the start of the hole, so I'm now ready to put in my 20 millimeter counterbore. Rightio. Now I'm at a point where we are ready to start cutting those threads. However, before we do, I need to have a bit of a think about what my next operation is going to be after that. So I need to part off a lump of this rod. It's quite a large rod. I can't continue to work with it at its full length. So I need to be able to part a fair bit of that off, and to do that is going to require that I have a live center like that in the lathe so I can support the far end of the job and part off without causing a great deal of chatter and problems. Parting is a pretty hard job on a machine. So I do need that. However, the hole that I've drilled here is just a plain hole at this point. We've just drilled a hole. There is no edge treatment to the entry point of the hole. The angle of this live center is an included angle of 60 degrees. So if I get a small boring bar and I fit it to my machine, I'll be able to adjust the angle of my compound to 30 degrees from horizontal and do a chamfer on the inside of that hole that will match my live center. It's important that the angle does match, because if the angles don't match, you're not really improving on the rigidity of the supporting edge over just jamming the live center in a square hole, which is not ideal. Rigidity for metalwork is generally very critical. One of the major differences between machining things made out of timber and machining things made out of metal is that metal has a much higher demand for rigidity. So move that around. I'm going to reset my compound to 30 degrees. 30 degrees. Tighten that up. Want that to be parallel to the bed. Ready to go. Now, just like when we were doing a facing cut, we're not going to be able to get pretty aggressive with this. We're going to have to do fairly light cuts because the metal is still a long way away from being supported adequately. Even though we have a fair bit of it in the chuck, it's still a long unsupported span, and so chatter is likely if we get too carried away. So, I'm up close to the work. Going to get really close to where the chamfer needs to begin. I'm going to continue going backwards and forwards with my compound like this, and come back out until I'm just cleaning up that edge. Fairly light cuts. Now the surface area that is left behind by this, I'm getting a small amount of chatter there, I can hear. The surface area left behind by this particular cut will determine how rigidly it's being held by the live center. I can afford to have a pretty large chamfer because I'm going to be cutting a thread in this hole, and having a chamfer on the start of a threaded hole is usually pretty nice anyway. It makes the screw much nicer to screw in. It's also a good deburring procedure, stops people from getting cut on sharp bits of metal. Okay, that's good. Did a nice light cut for the finish so that I'm not chattering too bad. Just bring that out of the way and check that my center fits happily. And it does, and we are now supported. So I shall set up to do the parting, and then we can, no actually, before we do that, whilst we're in the lathe, I'm going to cut the threads first. So that chamfer, even though I cut a thread, will still be in position, allowing us to put our live center in later, but I'm going to cut the threads now because those holes are on axis with the machine, and so I can leave the metal in the machine, hold the tap with my collet chuck and cut the thread. So I'll set up to do that. I've fitted my collet chuck with a M12 by 1.75mm pitch tap. This one's a bottoming tap, which means it doesn't have a very shallow taper at the start of the tap for beginning the threaded hole. It will thread right to the bottom of a hole fairly reliably, within 2 or 3 threads, depending on the size. But the cost of that is, without that shallow angle, you'll end up having a tap that's very difficult to start in the hole, usually. Contrast, we have here, hopefully that's visible. Let me come up closer to the camera, that'll help. I have here a pair of taps. Let's compare the two. I have a pair of taps, if it will focus. I have a pair of taps These are both my 3/8 16 NC thread taps, and you can see the start of the top one there is very steep. That angle is 2 or 3 threads worth of angle, and the bottom one, which I believe is an intermediate, I don't think it's a starting tap, it has a much gentler angle on the first few threads. This one's probably got about 6 to 8 threads or so of tapered lead in before you get to the tap profile proper. The bottom one is much nicer to start, much nicer. However, it won't tap to the bottom of the hole. The top one will, as close as reasonably practical to the bottom of the hole. If you're dealing with a project that calls for a thread to be right down to the bottom of a hole, then you probably need to consider the actual design of the project and whether it needs remedying. When you're cutting a thread, you are going to have chips of metal floating around from the thread cutting process, and so if you're being asked to thread right to the bottom of the hole, there's not much space left for those chips or clearance for the tap, for lead-in angle, or any of the general concessions you need in order to produce things reasonably well. So as such, if you run into a project that's calling for a thread to the bottom of the hole, you might need to consider re-engineering the project to develop yourself more space. Before I get real carried away driving this tap into the job, I am going to take a moment and a whiteboard marker and a ruler to mark out the depth of the hole I'm working with. The reason for doing this, I wouldn't normally stress about this too much, but if I drive this tap in, I'm just going to make a mark at 20 mil. If I drive this tap in and I get to the bottom of the counter bore, so remember there's 2 steps in this hole, there's a chance that if I kept digging, the tap would probably continue to cut a 12mm thread, even though the hole for the smaller part of the hole is 8.5 or 8mm rather. I don't particularly want to do that. That's the part of the job I'm trying to keep. So I'm going to make a mark just so that I can ensure that I'm going to stop at the correct place. Now, this is another benefit of collet chucks. I'm holding the tap in a collet chuck. It tends to hold taps and other tools very, very nicely. You wouldn't probably get away with this in a 3-jaw Jacob style chuck, particularly given that this tap has a reduced shank. These are examples of reduced shank taps too. If you're ever buying taps, I highly recommend getting reduced shank tools, because if you drive a tap all the way in, you get quite deep with the hole and it's time to remove the tap, then you have to unthread it all the way back out. But if you have the luxury of being able to just continue screwing the tap, you can go right through and the tap will fall through. Non-reduced shank taps, you don't have that freedom. Now, some people would be tempted to turn the machine on and drive this tap in under power. Being brass, you'd probably get away with it. I'm going to not do that, because the driving it under power for a hole that is of limited depth means that there is a chance I will overdrive it and go in too deep, and I don't want to risk damaging the part. Just relocated the camera so I've got some space to swing things around, but with a hand on the chuck, I'm going to turn the workpiece. I'm going to push the tailstock in unlocked. I'm not going to have it locked to the bed. I'm just going to let the tailstock, the weight of the tailstock, support the tap and hold it in the correct alignment, and I should be able to just drive it in. Brass always makes a terrific noise. Oh, pretty hard work. Use the chuck key, you can hang on to it a bit better. Now, there's not a great need with brass to go backwards as you're cutting in. Brass tends to self-chip fairly well, so I'm not too stressed about clogging the tap up. The tap is also dry. So in cases like this, if you were to add lubricant, you'd probably hurt the situation more than you'd help. You would be making the tap quite sticky, and all the chips would tend to clog up within the flutes of the tap, and that would probably be counterproductive. It is still quite tight. There will be some thread cutting on the way back out, which is unfortunate, but see how we go. Got 2 threads to go. Just about there. Yeah. Ooh, that's unfortunate. So I've broken the taper on the tailstock. I'm still loose here. Just give it a good smack. It should be okay. I'm up to my line here, so I'm going to wind my way back out now. Should get easier and easier. Yep, I might be able to ditch the chuck key. Unfortunately, I don't have a reverse on this lathe. It is something I'd like to do one day, but and we are free. Now I'm just going to double check that that's happy with a 12mm bolt if I can find one. I don't have any handy. That'll be okay. That thread should be fine. And we're pretty close to our shoulder, should be good. I'm going to cut a threaded stud on the lathe to support this piece of metal. That stud I'll probably make 15mm long or so, just to make sure that I'm not running into the bottom part of the thread where it is not correctly threaded. We just want the threaded part that's right, full depth of the tap, and we want this face, which we've already faced off. Those will be our locating features. With that part of the job completed, we're now ready to break down this setup and insert our tailstock, our live center, so that we are ready to start parting. I'm going to remove my collets, just about due a bit of a tidy up here. Put some collets back in the rack. There's there. We're done for drilling and... oh, we're not done for tapping actually. There is one tap to go. We need to tap our 3/8 N16 hole, NC16. So this one is 7mm on the dot, which is nice. Should be able to go straight to the correct size collet. Now we're going to do exactly the same process we've just completed and tap the innermost hole. Because I'm doing this with the lathe and the tailstock and other associated supporting components here, I don't need to worry so much about using the tapered start, a beginning or tapering tap. The bottoming taps will work fine because the machine is holding the tap in alignment. Might go a bit tighter on that. The taper tends to help a great deal. Oh, only just clearing it. Very close. You only need the taper for when you're cutting by hand. It tends to help to get those taper to start in the thread correctly. Exact same squeaky noise as before. This time we're going to tap until we are at the bottom of the hole. This one takes less effort because it's a smaller thread, which is good because I'm working up a sweat. Would be getting pretty close. Now I'm not sure I'm at the bottom, but I've just about run out of collet chuck stick out. So what I'm going to do is abandon the collet chuck. Nearly. Going to abandon the collet chuck. I've left the tap in there. I'm going to get my tapping wrench. I can reach it with half a motorcycle in the way. Just a standard tap wrench. I have to move this a little bit because the light is in the way. I'm just going to hold it with that, and that gives me actually pretty tight. I think we're pretty close to the bottom of that hole. Oh yeah, it feels pretty tight. I would say we're probably there. If we're not at the bottom of the hole, there is a pretty reasonable chance that we're bottoming out on a bunch of chips at the bottom of the hole. So what I might do is give this a blow and then drop the tap back in there just to double check that we're not too shallow. You should always be careful with compressed air, use it with goggles. Let's say we're pretty deep. Just clean my tap off a bit. Now, I'm going to bottom this tap back out to where it was. I'm going to measure how much of the tap is sticking out, so that way I've got a good idea of how far from the bottom of the hole I'm actually at. Now, oh yeah, got a little bit more out of it, so let's say we were resting on chips. I'm going to take that off. I'm going to measure. I've got 30 millimeters exactly sticking out. I know that that hole is 45 deep. So now, knowing that I'm 30 millimeters of tap sticking out, I can measure the rest of the tap and figure out how deep into the hole I actually am. So the whole tap is 75, so 75 minus 30. 75 minus 30, 45. I am at the bottom of that hole. Make sure it's clean, and we're now ready to set up to part. Now here with my live center in position, and I'm about to mount a parting tool into my tool holder, which will be probably just out of shot. I can see a bit of it. So I'm going to use this parting tool because it's my carbide insert parting tool. It tends to be a bit more reliable to get things going. It's a more rigid tool than the high-speed steel tool that I have. However, the high-speed steel tool has much better reach. So I'm going to start the hole with this tool, and then I'm going to swap back over to the high-speed steel tool. I'm going to set my tool so it's plunging vertically into the job. I'm just going to compare it visually to the cross slide of the machine. That should be fine. Now, before I get real carried away locking the tailstock in position, I need to actually measure where I'm going to part this off. We decided on our little mud map that we're going to do 50 millimeters. I'm going to part it exactly 50 millimeters to start with, just holding my ruler up against the edge of the parting tool, the end of the parting tool and the end of the job. 50 mil. Tailstock can come in. And we should be ready to part. Now, I'm not sure how this is going to enjoy the speed that it's on. It might part okay, we'll see how we're going. But it may require some adjustment to turning speed in order to get a chatter-free cut. Parting on lathes this small can be quite challenging. So when in doubt, there's plenty of scope for changing tool geometry as well as cutting speeds and RPM of the lathe in order to get things to work properly. It is doable, so long as the machine's not worn out. So let's see how we fare. It's not cutting great. I've got a really large burr coming up on the edge of the cut, which indicates to me that I'm probably not dealing with a particularly sharp tool. It's probably either due for a regrind, and you can regrind carbide inserts if you're a bit of a tight ass, or I can flip the tool around and start using the other side, but it seems to me that it's probably blunt. I'm just doing it here under hand power. It's sort of scraping a little tiny bit of material off, but it's not cutting like it should without huge tool pressure. So I'm going to spend a few minutes to remedy this tool, and I'll come back and complete the cut. So back from repairing the insert, what I've done is I've flipped it over. So I've gone to the other end. These are two-ended inserts. You get two cutting edges per insert. Then you have to throw it in the bin and get another one. Incidentally, actually, don't throw carbide inserts in the bin. They're worth quite a bit recycling. Carbide's pretty expensive stuff to work with, and having it in this form apparently is quite recyclable. I also tend to hang on to them because you can use them to make your own custom carbide tooling. So if you braze carbide to a bar of steel or whatever you've got handy, you can make your own custom shaped tooling for particularly odd jobs where required, which I've done from time to time. It is a handy thing to be able to have that sort of metal lying around for practical use. Anyway, I also ground the front of this tool very quickly on my diamond wheel. What I've done is steepened up the front rake, so it was a bit steep. I've brought it up more vertical. Not quite vertical, probably 3 or 4 degrees away from vertical. That helps prevent chatter. On Hercus 260s in particular, chatter is the enemy. It's very easy to develop chatter problems when parting, and so you take a lot of measures to get rid of it. The top rake, top face of the tool, is neutral on this particular insert, and it also has 2 little tiny ridges on it that might be visible in the camera there. They help prevent chip welding to the top of the insert, and they help keep the chip clear and encourage a round chip to break off. With steel, that becomes very, very useful to have. That little tiny pocket in the middle of the insert means that you can get lots of lubricant in there. I sometimes even use this. I have a misting attachment, so you can spray misted coolant onto the cutting edge of the tool, which is pretty handy if you're doing steel. Just like with tapping though, with brass it's not really required. Anyway, with the tool geometry sorted out and my rather noisy car driving off the driveway, let's give it a test cut and see if we've improved the situation. Much lower tool pressure required, muffier to cut in, absolutely an improvement. Now I'm not going to go too deep here. I don't want the sides of the cut to start dragging on the sides of the tool. That will create a situation where there's a lot of increased drag on the tool. So now that I've done a pretty reasonable cut, I'm going to go a little width of the tool to the side. So I've now got a double wide parting slot. In this particular instance, I'm going even deeper than I did on the first one. Just about out of depth on the tool. Just started to rub on the holder, so we're out of depth. Let's give it a quick clean up. I've left about 8mm left in the center of the cut. I'm going to bring this other one down because this is my nicer holder. A little bit of chatter, but manageable. Okay. Well, I've got the tool handy and my compound set to an angle. Just going to really quickly chamfer off that that burr that was formed by the blunt tool. So yeah, that tool's much happier now. And I shall get my high-speed steel tool and set up to cut the rest of that parting job. I've just finished setting up the parting tool. I've had to shim it because this is a high-speed steel tool. The height of the cutting edge tends to vary a bit as you sharpen the tool away. I've got a good amount of negative top rake here. The tool's leaning into the cut. And a relatively vertical front edge. That may need to change if I'm changing different materials. That profile is probably more suitable for steel, though brass does like having negative top rake, even on regular turning tools. It tends to respond quite well and leave a nice surface finish. In this case, I'm happy with that geometry, but it did need to be lifted up, so I've shimmed the tool. It's at its upper limit. This is one of the reasons why I'm not a massive fan of using my high-speed steel tooling on this lathe. To fix this, I would have had to have sharpened the tool back a fair way if I needed to get any more height increase. Or I could start shimming the tool post, which is not ideal. It tends to leave things less rigid than they should be. With that done, bring my tailstock back in and tighten it. I'm going to check that my tool clears and goes in nice and straight. I am pretty parallel with the cross slide, so fly's about to cop it. I am ready to turn. Now I'm going to get to a point where I nearly cut this part off and I would like to remove the tailstock. Continuing to cut gives us a huge risk of chatter because we're so far away from the chuck and we're unsupported at that point. But I'm going to do it as late as possible so that I'm left with a very small shaft of material to part away. Actually, in light of that, I'm going to actually reduce my tailstock pressure to prevent the part collapsing in on the cutting tool. To help avoid that situation, we have left ourselves a double wide groove. So in theory, it should be able to collapse a little bit, as all materials are elastic, but not grab the tool so bad that it will rip the tool off the end of the holder. Now I'm a fair way out here. I might actually bring that back in just a little bit. There's no need for the tool to stick out any further than it has to. So I might come back maybe that much. I'll just check that. Yeah, that's probably about right. And we'll nip that back up. Most tool holes don't need to be crushingly tight. This one here has got a cone, a wedged shaped object that holds the tool into its little groove, and a little bit of pressure with a spanner means the tool is quite tight. So let's see how we go. The tool is relatively sharp. I should have checked that before I got carried away. It's cutting fine. I'm down to about 3mm left. Back my tailstock out. The center has stopped turning, but it's just barely there. I'm going to hold this with my hand, just gently with my fingers, and there we are. That can sit there. Just going to finish that cut. Whilst I'm here, do a bit of a clean up. I'm going to swap to my cutting tool very quickly so that I can face the end of this rod and center drill it. I don't need to do that right now. However, if I do it now, next time I need this rod, let's say I need to part something off, which is quite likely given that it's a fairly long rod. If I need to part something off, I've already got my center drill hole in place, ready to go. So I'm saving myself a bit of work later on. I might not be set up to do that sort of job straight away. It means that I can get to work a little bit quicker. So I'm going to quickly face this off. Little nubbly bit's gone. Now just gently do a cut of the whole face. facing done. I'm going to center drill it. And that rod can now go back on my scrap shelf, my stock shelf, for another day. We might call it a day there. I'm going to make a video that comprises of these clips up to now, but tomorrow, or whenever I next get around to filming, which will probably take a day or two, I'm going to start working on the mandrel that will support our piece of material on that threaded hole. I'm going to work on the mandrel that would support that so that we can commence preparing the end of our job to be turned into a sphere, then turning into a sphere and parting it off. Until then, I will see you next time.